Hello everyone, and a very warm welcome to the class. Today we're going to tackle a very important topic from our Unit 9, Ray Optics and Optical Instruments, and that is refraction through a prism. Now I know many of you find this topic a little bit tricky, but I promise you, by the end of this session you'll understand it so well that all your fear will be gone and you'll be fully prepared for your exams.
So what's our game plan for today? Well, first, we'll start with a really simple question to get our brains warmed up. Then, we'll trace the exact journey of light as it goes through a prism. After that, we'll look at the all-important prism formula. And don't worry, I'll make it super easy. Then, the most crucial part, how to avoid those silly mistakes in the exam. And finally, we'll summarize everything and see how it connects to other topics. Ready? Cello, let's begin.
Okay, so before we can even talk about a prism, we have to ask a more fundamental question. A very basic question. Why on earth does light bend at all? What's going on there?
I'm sure you've seen this, right? You put a straw, or maybe a pencil, in a glass of water, and it looks like it's broken, or bent, right at the surface of the water. This everyday observation, this is the key to our entire topic. A prism is basically doing the exact same thing, just in a more controlled, structured way. And this bending of light has a proper name, as you know. It's called refraction.
So how do you remember this? I have a fantastic analogy for you. Just imagine you're driving a car on a nice, smooth pucker road, okay? And suddenly you drive it at an angle into a patch of thick, gooey mud. Now what happens? The wheels that hit the mud first will slow down, right? But the wheels on the other side are still on the road, going fast. This difference in speed causes the whole car to turn. Light behaves in the exact same way. The smooth road is like a rarer medium, say air, and the thick mud is like a denser medium, which is the glass of our prism. Simple, isn't it?
Right then. Now that we understand why light bends, let's get to the main event. Let's trace the exact path a single ray of light takes when it travels through a good old triangular glass prism. Okay everyone, eyes on the screen. Look at this diagram very carefully. This is the standard ray diagram that you absolutely have to know for your exams. You have to be able to draw it. You can see the incident ray PQ hitting the prism, the refracted ray QR traveling inside, and the emergent ray RS coming out. And notice all the angles are labeled I, R1, R2, E. We'll get to all of them.
So let's break this journey down into simple steps. Step 1. The incident ray PQ comes and hits the first face, AB. Now it's going from air to glass, from a rarer to a denser medium, so it bends towards the normal. Step 2. This bent ray, QR, travels straight through the glass. Step 3. It then hits the second face, AC. Now it's going from glass back to air, from denser to rarer, so this time it bends away from the normal. And this ray that comes out is the emergent ray, RS. So the key thing to notice is that light bends twice, once when it goes in and once when it comes out.
Now think about it. If the prism wasn't there, the light ray would have just gone straight, nah? But because of the prism, it has come out in a totally different direction. So the angle between the original path and the final path is what we call the angle of deviation. We use the Greek letter delta for it. Basically, delta just tells you how much in total the prism has bent the light ray.
All right, now for the part that I know can seem a bit intimidating, the formula. But please, don't worry about it. We are going to break it down so simply you will find it's actually quite logical. And this is the formula you will need for all your numericals.
And here it is. This is the prism formula straight from your NCRT textbook. The refractive index, N21, is equal to sine of A plus dm by 2, the whole thing divided by sine of A by 2. Please take a moment, look at it, and burn this into your memory. You have to know it exactly like this.
Now, a formula is useless if we don't know what the symbols mean, so let's quickly understand them. N21 is just the refractive index of the prism material, which is usually glass, with respect to the medium outside, which is usually air. A is the angle of the prism. That's the top angle of the triangle. And dm is something very special. It's the angle of minimum deviation.
So what is this minimum deviation? See, the angle of deviation, delta, actually changes depending on the angle at which you send the light in. But there is one specific angle of incidence, just one, for which the deviation is the smallest possible value. It's the minimum. And at this special condition, something beautiful happens. The ray inside the prism, QR, becomes perfectly parallel to the base of the prism, BC. It's a condition of symmetry.
And this graph from your textbook shows this idea so perfectly. Look, on the x-axis we have the angle of incidence, I. On the y-axis we have the angle of deviation, delta.
As we increase the angle of incidence, you can see that the deviation first decreases, and then it hits a lowest point. That lowest point is our dm. After that, if you increase I even more, the deviation starts increasing again. See that U shape? That's the key.
Okay, Cello. Now for a very, very important section. Let's talk about the silent killers. These are the common mistakes that I see students making year after year in their exams. Paying attention here will save you a lot of marks. I guarantee it.
First big mistake, and it's a very common one. Students just assume that the refracted ray, QR, is always parallel to the base of the prism, BC. This is absolutely wrong. Please write this down somewhere. The ray is parallel to the base only in one special case, at the angle of minimum deviation. Only when delta is equal to dm. At any other angle, it is not parallel.
Here's the second common mistake. People think that for every angle of incidence I, you get a unique angle of deviation delta. But just think back to that U-shaped graph we saw. If you pick a value of delta that's not the minimum and draw a horizontal line, how many times does it cut the graph? Twice. This means that for any given deviation, there are usually two possible angles of incidence that will give you that same deviation. The only time it's unique is right at the bottom, at the minimum point.
Great job, everyone. We're almost at the end. Let's quickly summarize everything and connect it to the bigger picture of optics so you know exactly where this piece of the puzzle fits.
See, this topic is not something separate or isolated. First of all, it's a direct application of Snell's law, which you've already studied. In fact, the big Prism formula is derived by just applying Snell's law 2 times, once at each face. And second, this is the foundation for our very next topic, which is dispersion. Once you understand how a prism bends one color, you're ready to understand how it splits white light into a whole rainbow. See? It all connects.
So to wrap it all up, here are the key summary points for your exams. 1. A prism bends light twice, causing a total deviation, delta. 2. This deviation depends on the angle of incidence. 3. The deviation is minimum, dm, when the ray passes symmetrically. And 4. The prism formula is the magic key that connects the refractive index n, the prism angle a, and the minimum deviation dm. Feel free to take a screenshot of this for your quick revision notes.
And I'll leave you with a final thought to ponder. Today, we learned exactly how a prism bends a single color of light, let's say a red ray or a green ray. But what do you think will happen if we shine a beam of white light, which, as you know, is a mixture of all the colors through that same prism? Think about it, because that question is the perfect gateway to our next beautiful topic, dispersion. Thank you for your attention.